let's continue with the torsion. And in this portion, we want to find out the relationship between the torsion or torque with the angle of twist and the shear stress. And with that, we go to the torque. So let me go back to the cross section here as we defined earlier. With that torque applied, then with the area small blue part in the cross section, then we can have the load from the torque. We call that here delta F on that members. So on that members, if we take the integral of all the moment of that delta F about the center, if we take that integral, we will get the torsion T, because that torsion T distributed throughout the cross section, and that realized with the force delta F in the small portion, that blue portion that I show it in cross section there. So from that blue portion, the area that I define for that blue portion is delta A, the area of that small portion. So from that one, we will have okay, let me put it down in here with the cross section there so that we can easy to visualize. So if we have the blue portion and any random blue portion there, so we call that areas is delta A areas, and if the torsion apply on that member is T, then it will realize with on that portion with the delta F, the force delta F, and the distance radial distance from the center to that member we call it rho. Everyone see that? So that what I realized from the cross section that I just show you, but it's too busy in that cross section. We just break it out to here so that we easy to visualize. So from that, what is the torque that we can have? Basically, the torque equal to the integral, the resistance torque equal to the integral of the moment of dF about the center, and it will be the force times the radius in the moment arm, right? So it will be equal to rho distance from the center to that portion times the force applied on that portion, dF, and at that portion, you see on that portion we have tau, right? On that member we have the torsion. On that member we have the tau, which is the shear stress on that portion distributed, and that is tau here, and you can see the tau distributed. If we get a portion in here, then the tau corresponding in that portion is tau, and it will be on the shear stress, as you can see, parallel to the cross section, and from that one we can replace the dF with tau times delta A, because you see the shear stress equal to shear force divided by the areas. So now to find out the force, we just say the area times the shear stress. So from that we can have it equal to the torsion, it equal to rho tau dA, the area dA. And what is tau? The tau in that equation we already have it equal to phi GL gamma. So let's replace that in here. So we will have equal to rho 5 G rho L, that is tau, and then dA. And if we simplify this integral, and you can see the constant can bring out the integral. Phi, if one thought, phi will be constant, g will be constant if the material is homogeneous and isotropic. L, the cross section is undistributed, is that what undisturbed, is that what we assume, then the L also constant. We can bring that out. So we have 5 G L constant bring out, and then the rho here we have rho times rho, it's rho square dA, rho square dA. We are getting there. If you recall in intro to kinetics, in engineering mechanics, when we find out the rotational equation, and at the end we check, I just write down here, but I will erase, moment about g, center of mass, equal to angular acceleration time m d r rdm r square dm. That here, if you have that here, r square dm, right? And in that r square dm, we, do you recall what we call this? Do you remember that is Ig? That is Ig. So the rotational equation is mg equal to Ig alpha. Ig is mass moment of inertia. Exactly the same as you can see. Look at here. This integral r square now replace with rho square with either radial distance, dm, the mass, it become a dA, the areas. So it also something about the moment of inertia. So in this case, it actually, we call that a polar moment of inertia. So let's call this one actually J, and that is the polar, because it, you see radial distance, rho is radial distance, polar moment of inertia. So it, as you can see, radial distance, geometry, areas, dA also geometry. So basically this is a geometry properties of the cross section. And like this one, it's both the Ig, it's both geometry, we see the radius in there, r square, dm, the mass, so material property, physical property of material. So let me erase that. But as you can see, that similar concept we apply in engineering mechanics in intro to kinetic here for the determine the area mass moment of inertia, and the one here is two equation look similar, just replace the r with rho and m with a. So with that we can simplify the polar moment of inertia at J, and that different from the other geometry properties, which is area moment of inertia. We already call it I, that's why we call it J in here, and I'm going to show you what is J in the next few minutes. But now let's simplify that one. Let's call that J. So we have T here equal to, the T is the torque at already J, so we can have it 5 G J over L. And from that one, as you can see, you want to find out the angle of twist. So you can have is angle of twist 5 equal to, angle of twist 5 equal to T L over G J, TL over GJ. So that, let's box that equation, the angle of twist. So this is angular distortion due to the torsion. And let me make you a similar equation that you learn in the first lesson, the first two lessons, which is the axial deformation. If you call the axial deformation, recall that axial deformation. I write down, but I will erase. Deformation is equal to what? Do you recall? P L over EA or AE. So you see the similar here. If I apply a loss P, then it go with the axial deformation delta. And if I apply a load T at the torsion T, then it go the angle of twist 5. So T, P, analogy, LL, the length, stem analogy. G, in the angle of twist, it analogy with the E, which is the yaw modulus, and G is shear modulus. So it's same it there. A is the area in the cross-sectional areas in the axial deformation, the green one there. And K, in this case, that is the polar moment of inertia, also the properties, geometrical properties of cross-section. So you see that that is a similarity between the axial deformation and the angle of twitch due to the torsion. So I'm going to erase this. If you want to review, go back to lesson, the first two lessons to have that one in there. Make sense, everyone? And also in lesson 4. So you see that the angle of twist. So bottom line, the torsion will create an angle of twist. And from that one, we also want to find out if it taught, then get the angle of twist. So what should be the associated shear stress, tau, that we draw here? Tau in here. And that what equation we have in here. Tau equal to 5 G over L rho. And now let's replace 5 with the equation we have, right? So you have tau equal to, so here 5 G L rho, right? So we have 5 G over L rho. So let's plug in 5 equal to what? T L over G J G over L rho. So as you can see, from that G cancel out, L cancel out. So from that we can have tau shear stress distribution through the cross section of the member with torque. It equal to T torsion over J polar moment of inertia rho. And the same that we define in there, it linearly distributed over cross section. It's the same here. If tau effects, then it T effects, torsion effect, J of course cross section is the same throughout the members. And then it only depends on the rho, which is the radial distance from the center to the point that you want to measure the torsion, the shear stress to the cross section in there. So from here we have that tau. So that is two important equations that we have it in there. So we want to the last minutes here is we go ahead to define what is the polar moment of inertia. So J as the polar moment of. So in this class, I is stand for area moment of inertia. J polar moment of inertia. So from that one, it as you can see, it equation is integral of rho square dA, so that it fully depends on the geometric properties of the cross section. So from that we can have that here geometric properties of cross section. And as you can see here, if the J is big, then the 5 angle of twist is small. If J polar moment of inertia is small, then the angle of twist is big. So what does that mean? If the same torsion apply, if the cross section have a smaller J, then the angle of twist is bigger, and vice versa. So what does that mean? The J is resistant to the twisting, resistant to the torsion. Similar to, if you recall, in the rotational motion, the mass moment of inertia resistant to angular acceleration, right? And then you also talking about the area moment of inertia in the previous lesson is resistant to the bending moment that we are going to talk later on. But that you see the different moment of inertia for different purposes. So let's put it down here. It's resistant to twisting. And you can see bigger G, phi will be less. So it will be twisting. And then, like I say, we only apply for two scenarios. Both are circular section, but solid or hollow. So for solid circular section, then what we have, J equal to 5/2 C4, where C is the radius. What is that? Why we have that one? If you forget about that, go back to the, again, moment inertia for common geometrical shape. If we go to the circle, we have Ix, Iy, basically that is the area moment of inertia, and J about the O, as you can see here, 1/2 pi R4. So that is the J in here is polar moment of inertia for the cross section. So go back here, we have C4. And then for hollow, this is for solid. And then we have for hollow circular cross section, just like lightsaber Star Wars sword that I showed you in the demonstration. So circular section. Then we have J equal to 5/2, and then we have C outer power 4 minus C inner circle, C inner circle power 4. So what is that about? If we have a cross section here for that one, so that is C we are talking about, C. And now if the hollow circular cross section, if hollow circular cross section, then we draw with the hollow, so the C inner circle, basically here, that is CI, and the C for outer radius, CO. So that's what we have for the polar moment of inertia. So with that, we investigate relationship between the torque with the angle of twist and the shear stress, including its distribution over cross section, and then the polar moment of inertia, another geometry properties of cross section that resist to twisting. And we're done for today's class.